Alright, so ladies and gentlemen, today's class recording has started. So, to review a couple of the things that we talked about at the end of the class yesterday. We finally got to what we refer to as the quantum mechanical model of the atom, or the electron cloud model of the atom. That is the work of, among a lot of other people, but definitely Schrodinger, and that's sort of our main view of what the atom looks like today. So, if we had to describe the quantum mechanical model, or Schrodinger's model of the atom, what are the things we learned about yesterday at the end of class dealing with Schrodinger's model of the atom? You see a picture of it down there at the bottom. That might be able to help you out. Frank?
You can't calculate the exact location when
So let's start with the first one. Okay, so one thing that differs, that is a progression between Schrodinger's model and Bohr's model, right? Frank, we cannot know exact locations of electrons, right? We refer to that by what name? What sort of idea prevents us from knowing the exact location of electrons? We talked about in class yesterday. The uncertainty principle, right? Anybody remember the scientist responsible for the uncertainty principle? Nope, not Schrodinger. Heisenberg, right? So Heisenberg's uncertainty principle, okay? All right. So, Frank, we can't know exact locations, but what did Schrodinger do for us? Okay,
Not defined.
good, all right? So, we don't have defined spaces, but we do have areas of high probability, all right? And we refer to those areas of high probability as high electron density, or having high electron density. Okay? Good with that idea? All right. So looking at this picture down at the bottom, okay? That's Schrodinger's model of the atom. Nucleus in the middle, and Rutherford's experiment told us that the nucleus is real small. Okay, great. But what we see is then these dots around the nucleus represent the locations of electrons at some time in the past, right? Okay. Do we remember how Schrodinger determined his location of electrons sometime in the past? I know this is not a process, but we referred to it as something in class yesterday. Yes, he found the energy and he solved something. Do we remember what he solved? No. Not E equals MC squared. That part of it. So, Schrodinger's wave equations give us the location of electrons based on their energy, or at least the location of electrons in the past. Okay? And, like we discussed yesterday, when we look at the area surrounding the nucleus, we find that certain areas have lots of dots, and then other areas not so much. Right? And we'll see that pattern continue. And as we look inside of those areas that have lots of dots, we'll see that there are even more patterns sort of like contained within these bigger areas. And that's what we're going to work on over the next couple of days. Okay? All right, so let's fill in a little bit of the outline first, just so we have some background, although we talked about most of this already, and that's okay. All right, so today's and tomorrow and Friday's presentation we refer to as location of electrons in the quantum mechanical model. It's quote-unquote location, right? Because will we ever know the location of those electrons? No, right? We know areas of high probability. So, uncertainty in Schrodinger's wave equations, right? The work of Heisenberg and Schrodinger lead us to the conclusion that the exact location of an electron will never be known. Yeah, sometimes it's there, sometimes it's not. You can put it there if you like. So. Okay. Right. Based on the work of Heisenberg and Schrodinger, we come to the conclusion that we will never know exact locations of electrons. But Schrodinger's wave equations reveal areas of high, quote-unquote, electron density. If we, right, let's finish this up and we'll go that right. These areas of high electron density or high probability density we refer to as orbitals, right? They're not orbits like Bohr said, they're orbitals. They're kind of the location of electrons, okay? Is that good with where that name comes from? All right, so going back to this picture, right, Schrodinger's model, okay? We said that all those dots represent the location of electrons somewhere in the past, right? So think about it this way. Let's say, as part of some kind of an experiment, or maybe, like, I don't know, maybe your parents are, don't trust you, or for some whatever reason. I don't think any of your parents have reason not to trust you, but maybe they don't, all right? So you know how they can get that little app that is like track your phone, so like, you know, you can track where your phone is, right? So, let's say we had that app, and we tracked your phone for a week. And every, let's say, 5 minutes, your phone would send a signal to the app, and the app would record the location of your phone every 5 minutes for a week. We recorded all those locations, we put them on a map of Westlake. Certain areas of Westlake would end up with more dots than other areas of Westlake, right? Like what? Your house, school, right? Maybe if you have a friend's house that you go over kind of a lot after school to work on homework or whatever it is, right? Maybe you go hang out somewhere after school, whatever that may be, right? There are certain areas of Westlake where you have been more often than others, right? If, for some reason, in some unfortunate situation, you went missing, right? If you don't show up to school one day, where's the first place school checks for you? Home, right? Why? Because you've been there a lot in the past, so there's a good probability that you'll be there in the future, right? Keep in mind, though, just because that's where we've been in the past doesn't necessarily guarantee that you'll be there in the future. If you're not at school, is it probable that you were at home? Yeah. Is it possible that you stole your mom's car and drove to Mexico? Yeah. Yes. Possible, not probable, right? So keep that in mind. Electrons can be anywhere around the nucleus, but there are areas where they have been more frequently in the past, so we expect them to be there more frequently in the future. And these areas where we expect them to be, we call orbitals. All right? So, that being said, let's not go there. Let's go here. Okay? So, right, orbitals show up at not random locations around the nucleus, but, like we said, they are areas that have real high dots, real high collections of dots, representing places where electrons have been in the past. Okay? All right, so let's draw ourselves a picture. It's going to be a pretty complex picture with lots of pieces, and I have the ability to draw things in a way that you can't because I'm going to use this board, so I can like overlay things and stuff like that. So let's do the best we can. If it's not the best picture in the world, it's okay, but we're going to go with it. All right? So your picture is going to start with a set of X, Y, and Z axes. And you'll see that on the back of your sheet, right, you have one big set of X, Y, and Z, or one big X, Y, Z axis, and then you have a couple of small ones. So maybe you make a little bit more detailed pictures in certain spots. Okay? All right. So a couple things about this picture, right? First, the origin of this X, Y, Z axis, right, is going to represent what part of our atom? The nucleus, right? The nucleus is at the origin. And remember we said the nucleus is relatively small. Not relatively small, really small compared to the rest of the atom. Okay? So keep in mind that that nucleus is always in the origin of this graph. Okay? Are we good with me calling it XYZ axis? Are we okay with that, right? X-axis horizontal, I always call the x-axis horizontal. Y-axis vertical, and then the z-axis, right? Even though I've drawn it dotted, sort of diagonal like this, keep in mind that that z-axis comes out of the board or out of the paper towards you, okay? Does that make sense? That they're all perpendicular to each other. X and Y are perpendicular this way. X and Z are perpendicular this way. Y and Z are perpendicular this way. Are we okay? Are we picturing that in our head? Hold on. Okay. All right. So, x-axis, y-axis, right? This is 2 dimensions. Okay? Good with that? And you all know this from math class, right? X comma y, we can plot a space, blah, blah, blah. Okay? But the real world isn't 2-dimensional, right? The real world is 3-dimensional. So to represent that that third dimension, we need a third axis, right? All right? Does that make sense? Okay? So the one that has the rainbow tape on it is the z-axis, which in reality is perpendicular to the other two. It just comes, like if you're looking at your paper, it comes out towards you, all right? And then it also goes into the table underneath you, okay? But in reality, it's like this, all right? Now, I obviously can't show you this on your paper, because your paper is only 2-dimensional, right? So a lot of times what we'll do is we'll kind of make that diagonal line, all right? But remember, the dotted one is coming out of the paper towards you, all right? It's not diagonal like the rest of them. It's coming out of the paper towards you, all right? Well, let's talk. Okay, that's where we're gonna start. Okay. All right. So, if you had to take a guess, where do you think we would most likely find electrons? Where's the most probable location for finding electrons in an atom? Sammy. Close to the nucleus, right? 2 reasons why we can say that close to the nucleus would be a good place to start, okay? What are 2 reasons why we might find atoms or electrons close to the nucleus? Okay, protons have a positive charge, electrons have a negative charge, there's some attraction there, right? What else is another reason why they might be close to the nucleus? Very good. There's one word I want you to change in there, right? It's not a lower electric charge. They all have the same electric charge. What did Bohr tell us about the location of electrons? Lower energy, right? So it's attraction, positives and negatives, but it's also lower energy, okay? So what we find is that, oh, by the way, sorry, before we go any further, see this picture right here? Okay? That's where we're going to end up eventually, okay? I know, it looks like a total mess, but we'll break it down piece by piece by piece, okay? So don't freak out, all right? All right, so we're going to start with this, okay? A small sphere that surrounds the nucleus, okay? This is our first orbital. Keep it small, because remember that picture I showed you before? That's where we're going to end up. We got to draw all this stuff on top of it, okay? So, a small sphere that surrounds the nucleus. No, that's good. You're going to see that I'm going to draw, like I showed you, Chris, I'm going to draw, all my pictures are going to be like right on top of one another, okay? Because I can do that on mine, and you might not be able to, okay? All right, so this is our first orbital, okay? It has the lowest energy electrons that you can have. And as a result, this is where we are most likely to find electrons, okay? But it's very much like the bullseye on a target. Okay? While it's the goal and it's the lowest energy that electrons can have, will we find a lot of electrons there? Seems like a good idea, right? Low energy, attracted to the nucleus, fill it up. But there's a problem. One of the reasons why electrons are likely to be found there is because they are attracted to the nucleus. But negatively charged electrons are attracted to the positive nucleus. But what happens if we put too many of them in the same spot? They are attracted to the nucleus, but they start repelling each other. All right? And so, while this is the most likely space to find electrons, we won't find too many electrons in that space. Only a limited number of them. Okay? Good for starters. All right. So, what does that mean? Well, we got to go to a new place, right? Here's the next place. It's another sphere. Now, keep in mind, this is a three-dimensional picture. The first sphere you drew, now, if you guys would like, we can talk for now, and then maybe as we go through and explain it a little bit more, you can add your drawings. How's that? Okay? So why don't we just talk for now, and then we'll add our drawings a little bit later on. Okay? All right, so keep in mind, this is a three-dimensional drawing. The first sphere, the yellow one on my picture, surrounds the nucleus. This one surrounds the yellow sphere. The red one is a hollow sphere. It surrounds the yellow one. Okay? It's the next most likely place we are going to find electrons. Why? Well, it's still pretty close to the nucleus, but it's a little bit outside of those electrons that are in the yellow sphere. And so the electrons sort of settle in just outside that yellow sphere into this red hollow sphere. Okay? Good there? All right. But now that we've moved outside of the very, very, very middle part of the atom, we have a little more space. So now electrons can still kind of be close to the nucleus, but kind of be away from each other. All right? And so what we find is that a couple more spaces start showing up. Here's the next one. Okay? It kind of looks like a figure eight, where one side of that figure eight is just outside of the red sphere, and the other side is just outside of the red sphere, both along the x-axis. Okay? Good so far? But if we can put something on the x-axis, where do you think else we can put it on? The y-axis. And then also ultimately the z-axis, right? So you'll see in the next 3 pages, right, you got this one, then you got this one, and then we got this one. Okay? Now, something to keep in mind, you'll see here, okay? I want you to pay attention to shapes and colors. Okay? Notice none of the ones that I just put on are yellow, but they're all red. Even though some of them are different shapes, they're all red. But the last 3 that I just put on, right, this one, and this one, are all exactly the same shape and the same color. Good there? Okay? All right. Good so far? Okay. But now, we have filled up our x-axis, our y-axis, and our z-axis, right? Nowhere really else we can put that. Because remember, we're still pretty close to the nucleus at this point in time. So it's still kind of crowded, all right? So the next thing that shows up is this one. Okay? Notice a similar shape to what we've seen before, but a new color. Right? Again, this one is going to be a hollow sphere, and it's going to cover all of the stuff inside of it. Okay? It's the next most likely place that we will find electrons. As we start getting farther and farther and farther away from the nucleus, we start, or these electrons, start having to do a little dance. And there's two rules to the dance, right? One, try to get as close to the nucleus as you can. Try to get as close to the nucleus as you can. Sorry, I didn't come out exactly. Okay? Two, try and stay away from other electrons. Right? Those are the two rules that they're trying to follow. And so we start seeing them settle into places where they can, one, be away from other electrons, but two, still try to be as close to the nucleus as possible. Okay? All right, so there's our next level, or there's our next space. And remember, on a Schrodinger picture of the atom, these would be all a bunch of dots collected in that space, right? And then there'd be a hollow sphere of dots that surrounds all these dots. Remember, these are all based on probability. Likely places where we will find electrons. Why? Because we have found them there before. Okay? All right. Next space that shows up. Ready? Okay. Next one after that. All right. Pattern. Are we noticing a pattern? Okay. Now, here's where it starts to, well, it doesn't deviate from the pattern. It's just the pattern isn't complete. As we add more space, now there's more and more places for electrons to sort of settle in where they're close to the nucleus, but still away from other electrons, right? The red ones that look like figure eights are stuck x-axis, y-axis, and z-axis because we're still really close to the nucleus. But now with these blue ones, we're a little bit farther away. And as we move farther away from the nucleus, there's other spaces that become available because there's more space for them to spread out. And so now we add another one, and it looks like this. Okay? Now, notice how this one is a figure eight, and this one is a figure eight, and this one is a figure eight, but they're all separate from one another. Okay? This one, okay, comes together like this. It's like an X, and it's all one thing. You can say, well, wait, isn't it four separate things? No, it's all one thing. Okay? That's a little confusing, I understand, but that's how it works. Right? And notice where it settles in. Where did it settle in on our axis? In between the x and the y axis. Right? And if one of these x's can settle, oh here, let's do this. So if we have an x and y axis, right, it settles in here, 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 and here. Does that make sense? Okay. If one of them can settle in between the x and the y axis, guess where else something can settle in? Between the z and y axis. So like here, here, doesn't help if I twist it, right? Here and here, and between the x and the z axis. So we start seeing these things start settling in around those figure eight ones that are on the x and y axis. Okay? Good so far? All right, remember, just a picture right now. We'll talk what the picture means as we go along. Okay? All right, ready for the next one? All right. All right. Ready for the one after that? Can we make an educated guess about the one after this is going to be? Figure 8. Figure 8, figure 8. I just put them up at the same time there. Okay. All right. Now, I didn't draw this one because I ran out of time before you guys came to class. I apologize for that. Okay. What do you think the next one would be?
A big circle.
Nope. Remember, the X's showed up, right? So the X's would show up then as well. Okay. All right. Do we see kind of, sort of, maybe how it all sort of fits together? At least from an introductory level. Okay? All right. So let's start talking about this picture and let's start hopefully making some sense of it. Okay? Each one of these spaces that I just put up there is an orbital. Every single one of those things I put up there is an orbital. Okay? They have different shapes, they have different colors, they have different locations, but they're all orbitals. So what we try to do is tell one orbital from another orbital. Some are similar in shape, some are similar in color, but we have to tell them apart. And the way we do that is through something called quantum numbers. It's like an address for the orbital that we're trying to describe. All of you have separate addresses. All of you have places where you're most likely to be if you're not in school, right? You get the idea. Sophia's not in this room, so we don't have to worry about that. But anyway, so each of those orbitals has an address for that location. Okay? Each orbital has a unique set of quantum numbers. These numbers provide an address for that electron. Remember, it's not the exact location of an electron, just its probable location. Okay? And we distinguish each of those orbitals from each other with a unique set of 4 quantum numbers. Each of those locations, quote-unquote locations, each of the orbitals that I just put up on the screen has a set of 4 numbers that distinguishes it from all the other orbitals. Even though some of them have similar colors, even though some of them have different shapes, or similar shapes, each one has its own unique combination that distinguishes it from all the other orbitals. Okay? Good there. All right. So, let's talk about how we distinguish them from one another. So let's talk about the first quantum number. And we refer to the first quantum number as the principal quantum number. Notice it's principal, P-A-L, all right, not P-L-E, okay? And hopefully if we remember English, right, principal, P-A-L, means like the biggest or most important or something like that, okay? So this describes one of the big factors about each orbital. We use the lowercase letter n to represent the principal quantum number. And more than anything else, the principal quantum number describes energy. Okay? More than anything else, the principal quantum number describes energy. Meaning, orbitals that are closest to the nucleus should have low principal quantum numbers, and orbitals that are farther away from the nucleus should have higher principal quantum numbers. Why? Because what do we know about orbitals that are close to the nucleus? Lower energy. Whereas as we get farther and farther out from the nucleus, higher energy. Okay? So more than anything else, the principal quantum number describes energy. Okay? Oh, there you go. Are you sure? It's area, yeah, areas, orbitals, yeah. Change areas in letter C to orbitals, and well, that's what I had before. So more than anything else, the principal quantum number describes for us the energy of the orbital. Okay? Good so far? All right. If we go back to our picture, okay, any guesses about what would represent or what sort of tells us about the principal quantum number in this picture? Do you want me to go through the progression again? Here. It's like a flip book. Watch, ready? Okay, ready? Here we go. Load up. What tells us about the principal quantum number in this picture? What were you going to say? At least to get the ball rolling. You sure? So, what tells us about the principal quantum number? Not exactly. There's something more specific about the color. The color describes for us the principal quantum number, right? Here's the first orbital. It's the closest, right? Meaning it has the lowest energy. This one, just outside of the first one, it has the next lowest energy, okay? Now, here's where we distinguish a little bit more, right? And so these three, while a different shape, are still the same color, okay? Think about it this way. If we were really using our analogy of an address, right, the principal energy level would kind of be like the city that you live in, all right? There are lots of houses in Westlake, but all of the houses, I should say all of the houses in Westlake, but a lot of the houses in Westlake are very similar, right? They have a similar quality. That's what all the orbitals that have the same color are like. They have similar energy. Not all exactly the same, but similar. And then when we move outside of that area, now we have a different energy. Higher up, farther from the nucleus, higher energy. Okay? Frank, go ahead.
So, does that mean, like,
Okay.
and then the vertical one, they have the same principal quantum number?
Yes. So Frank asked, do these, and these all have the same principal quantum number? And the answer is yes. But guess what else?
Yeah.
This one has the same principal quantum number as well. Same color. So any orbital that is the same color as anything else is going to have the same principal quantum number. Okay? Good there? All right. I think that's a good natural break for today. So let's stop it there. Okay? And we'll pick it up tomorrow and talk about these three guys here, or girls, or orbitals, right? Talk about why they look the same, why they're the same color, but that they are in fact different. And so we'll start talking about those and distinguishing them from the other ones. All right? Good job today, everybody. It's a good start. We'll come back tomorrow and we'll work on the picture a little bit more. We'll add a little more detail, and then we'll start putting some numbers on it as well.